Hi there. Thank you for tuning into the video. My name is Dr. David Hall, and I'm a research fellow at the Queensland University of Technology, working within the Australian Centre for Robotic Vision as a part of a Robotic Vision Challenge research group. I would like today to give a small talk about whether or not our object detection evaluation norms are, quote, enough. Now, I'm not making this talk as a decree from on high to say this is exactly how things are wrong and how they should be done in the future, but I'm hoping that it is the start of a more broad conversation to be had both in the interactive sessions as part of this workshop, but also within our research community, trying to make sure that we are, in fact, performing our object detection evaluation in the way that is most beneficial to that object detection systems being utilized in actual real-world applications. So before I get going, I'm going to try and define what is this norm that I'm talking about and how do I define enough. So the norm that I'm talking about here is the classic structure that we have. We have a large data set, we apply our object detector to that data set, and we get some sort of score at the end. Typically an average precision score, mean average precision score, or the COCO version of mean average precision. And we generate our tables like this, and we get our method in bold at the bottom, and through that bold number, we say that our our object detector is the best object detector around. Sometimes we will go into a little bit more depth, looking at different IOU thresholds for average precision or different subsets of the data to try and get further inklings. But in the end, that big bold number at the bottom is what matters and determines whether or not we are good at object detection. And what do I mean by enough? Well, I'm trying to establish whether or not our evaluation norms are suitable for practical uses outside of challenges. So within the Australian Centre for Robotic Vision, we're very focused on using computer vision for robotics. And are our evaluation norms preparing us to create object detectors that are suitable for applications such as robotics? Do our evaluation norms give us enough understanding as to how we are getting better? And do we have any blind spots in our general evaluation protocols? So the structure of how I want to go about this is as follows, basically highlighting what it is that we have now, trying to highlight any potential issues that I've come across in my research in creating robotic vision challenges, and try and give my insights as to how we might go about addressing some of these issues. So what is it we have now? Well, quite a lot actually, and quite a lot of good things. So we have the ability with our standardized structure to be able to evaluate a vast swath of object detectors in different configurations and have large comparison tables saying exactly how good we are at specific data sets. And speaking of specific data sets, we have been able to continuously improve our data sets. Every time we get good at one of them, we introduce another one, getting bigger and with greater variety, which is very good. And our object detectors being able to perform well at multiple data sets is a good way of determining whether or not our object detector is good. And we've been able to, through this combination of data sets and standardized evaluation measures, we've been able to show a steady increase in object detection performance. And underpinning all of this, as I mentioned at the beginning, is the idea of a standard evaluation measure. And in our research fields, this is mean average precision. And I'm going to go into that a little bit more now because it is something I'm going to be trying to dissect and understand a little bit later on in the talk. So mean average precision. Specifically, I'm going to be talking about the variant used for the COCO challenge because I think that is the best example of an evaluation measure trying to give great insights into how well object detection is performing. So how mean average precision works is that for a given IOU threshold in a given class, we assign detections to ground truth objects that have the same class label as the ground truth object and IOU score greater than a given threshold. So here in this image, the blue dashed boxes are true positives and the orange ones are false positives. This is a standard way of looking at things that we'll be seeing throughout this presentation. We generate a PR curve over label confidence acceptance threshold. So with starting at the highest confidence detections, we plot the precisions and recalls as we quote, introduce each detection, so starting at 0.9, and then 0.8, 0.75, 0.7, etc., to generate this sort of PR curve. Then we smooth that PR curve to get rid of little wiggles that exist within the PR curve. We record our precision levels at different specific levels of recall. For COCO's version of MAP, this is 101 different levels of recall. And if a level of recall has not been reached, the precision is considered as 0. Then we repeat steps 1 through 5 across all classes and IOU thresholds, and we average all these precision results together. Now, this paradigm of average precision, mean average precision, has stayed relatively unchanged since it was first introduced back in the days of Pascal-Vogt. The version we have now through COCO has added extra bits to it, such as the averaging over different IOU thresholds as well as different classes. But this standard way of going about things has stayed pretty much the same for a long while. And that has been good for us because we've been able to see, we've been able to transition nice and easily from dataset to dataset, challenge to challenge, and see our progress over time. But are there any potential issues that might exist within our current framework? We've got our large datasets, we've got our evaluation measures, and MAP has served us very well for quite a long time. But are there any issues that might exist here? Now, again, warning, this is going to sound like I'm being particularly cruel to standard ways of doing things, particularly average precision. But it's more the insights that I've gathered in looking at things from a robotic vision perspective, looking at how we can take our object detectors, apply them in the real world, and whether or not our evaluation measures are properly letting us understand the strengths and weaknesses of our detectors in that context. So I'm going to split up the potential issues into a few little parts here. The first are problems that I consider outside standard object detection. So this is stuff that has its own research fields in and of itself. So this is things such as detecting, identifying unknown objects or open set detection, and detecting objects with spatial uncertainty or probabilistic object detection. These are both very important in applying an object detector to the real world, being able to say, oh, I don't know what this is, but I think that it is something, and being able to give some uncertainty as to where exactly you think something is. However, I'm not going to go into these in too much depth here because they are their own fields of research, and we are going to focus here largely on what I would consider as standard object detection, bounding boxes trying to detect known subset of objects. The second area that I would highlight is dataset bias. I'm not going to go into too much detail here either because this is a fairly well-known concept within computer vision research. Dataset bias being the issue that we might get too good at just doing our specific dataset as opposed to being more generally applicable. So overfitting to specific datasets is an issue. There's also just bias in the nature of the data that we are using for object detection. So everything is using data mined from Flickr, etc., which gives us a large amount of bias because the images being taken are taken by humans. They've got sort of generally pretty decent lighting conditions. Objects are often well framed within the image, and there are a set of common camera angles that every object is viewed from. For instance, you don't typically see the underside of a chair, or you don't see objects from, say, the perspective of a Roomba, which is very low to the ground. But again, this is an issue that is well known to the computer vision community, I think, and our solution has typically been to just create more data sets, more data, more variety as much as possible, which comes with its own inherent issues that you will never have enough data for everything, but is at least something that is known and addressed by the research community as a whole. What I want to focus on is a bit more of the things that I don't feel are as well focused on. And those are largely, in my mind, surrounding the potential issues that might exist with mean average precision as an evaluation measure itself. So I'm going to go, hopefully fairly quickly, through some of the potential issues that I see with MAP and how they relate to the application of object detection systems to real robot systems, and in interpreting them, the results from MAP to get a greater understanding of how object detectors work. So potential issues that I see in increasing importance are just the ease of interpreting results, the concept of evaluation absolutism, how meaningless certain label scores can be, and the way that they MAP can obscure some false positives. Again, this is all just stuff that I have found within my own research in creating evaluation measures for robotic vision challenges, but don't mean that MAP is inherently broken, just that there are some things that I think the community should be aware of and we can potentially move past as we go forward. So in terms of interpreting MAP results, I simply mean that MAP is rather dense to try and dissect. You're not just dealing with a single PR curve, you are dealing with several PR curves per class, over several thresholds, and it is an average of all of that that we are using to determine how good our system is. And exactly what, in what ways our detector is performing better can get a little bit lost in that because it is such a dense system. So for instance, if we were to compare two MAP scores, we can easily see that yes, this is the better system, but the question becomes, how is it the better system? Is it got better localization? Does it have improved label scores? Has it got more detections? It's a bit hard to tell. Now, one of the things that's really good about COCO's implementation of NAP is that through the multiple IOU thresholds, we can get something of an idea as to whether or not we are better at all levels of localization or just good at very basic localization. We can also get, with mean average recall, a sense of whether or not we are detecting more objects overall. And this is good, but it's still a little dense to go into. But this is, again, just a minor point that I just feel deserves a little bit more talk in the community, because we see a lot of tables with bold MAP scores, but I don't see as much of the deep interpretation as to how we are getting better results. That's often being left to a more qualitative analysis. And then I come to the next point, which is evaluation absolutism, which is a bit of a bigger issue in the context of trying to apply systems to robotic systems. So by absolutism, I mean that because we're using a precision recall curve, which requires true positives and false negatives, we can't have detections which are some degree of correct. They are either right or they are wrong, nothing in between. For localization accuracy, this comes about in the form of IOU thresholds, where you can have multiple different detections on a given object, but if you've got a set IOU threshold, like say 0.5, all of these have to be considered as perfect. They are absolutely right, which in a robotic setting in particular can be a bit of an issue, because we want to be able to say for certain whether or not we are detecting an object particularly well, we've got some wiggle room, etc. In terms of class labels, this comes across in terms of the use of label scores. So if we have two detections of a given cat, and the full probability distribution for that detector would have said that the left one is slightly more confident it's a dog, the right one is slightly more confident that it's a cat, when this is compressed down into the format that is required for object detection, a single label with a single score, we get one is dog, one is cat, one is totally wrong, and one is totally right. Which gives us no real wiggle room for label ambiguity. And it ties very closely into the next point that I would like to make, which is about how label scores don't seem to mean very much within NAP. They're used very heavily to create the PR curve, and detections which are higher in confidence will be considered earlier than detections with lower confidence, but the absolute value itself doesn't have any inherent meaning to it. So if I gave a situation of which detection here is better, there's no real way of determining that. It is either completely right, yes, it is a cat, completely wrong, and the score is just used to place it within the PR curve. And that can lead to situations where if we had an object detection situation like this, for example, it'd be exactly the same as if we squished all of the label scores between 0.9 and 1.0. Or if we squish all of those scores down to 0.0 and 0.1. The score itself doesn't matter, just the relative ranking, which doesn't make a lot of intuitive sense and would potentially lead to issues when directly applied to robotics, where in robotics, we are assuming that we are going to have a meaningful uncertainty level for whatever it is we're looking at. If we are 50% confident that something is a chair, we are only 50% confident it's a chair. If we are 100% confident it's a chair, we are certain that it's a chair. Now again, what I gave before was a fairly abstract example, but we can already potentially see what might happen thanks to this way of going about evaluation. If a label score doesn't mean anything, well, we already know that classification neural networks are poorly calibrated, despite the fact that our classification error has been reducing. And if a label score in and of itself is irrelevant, why should this change? Yes, this may affect the MAP scores in some slight way, but it's hard to say explicitly what benefit you are getting from having a well-calibrated detector. The final point that I'd like to make in terms of a limitation of mean average precision is that it can obscure some false positives. And this is potentially dangerous when you think about the context of robotics, where a false positive really means something. If you are constantly filling your images with false positives, then a robotic system may very well freeze trying to figure out what it is it has to do. So what I mean by this is that if we have a situation again like this, and we have our lowest true positive confidence is 0.2. If we flood this image with false positives of confidence 0.1, they aren't going to affect the MAP score at all, because in terms of the precision recall curve, they occur after we have reached a set level of recall. Once we have found our maximum level of recall, all subsequent detections, false positive detections that are from detections with lower confidence than that last level of recall confidence, these are going to be simply ignored in evaluation. And this, again, typically isn't much of an issue, because in reality, when we're using object detectors, these are extremely low confidence detections, but they don't necessarily have to be. Again, because the class labels themselves don't mean anything, if we had all of our true positives higher in confidence than our false positives, then we could move all of our true positives being 100% confident and all of our false positives being only 90% confident, and you'd have the same result. In fact, this situation is even more frightening, because in this situation under MAP, the score is perfect. This is a perfect detector, despite the fact that this sort of result would be catastrophic to a robotic vision system. And again, these are fairly extreme examples, and they aren't meant to say that MAP is fundamentally broken, but they are to say that there are hidden issues in there. And these can also spill out to how we utilize MAP in our actual object detection results. So for instance, let's look at results from two detectors, both of which have fairly good recognition of true positive objects, but one of which has a whole bunch of false positives. As you might be expecting by this point, the MAP is higher for the second detector. But what detector is it that we're actually looking at here? We're actually looking at exactly the same detector, but with two different label thresholds. Do we consider only detections with confidence of above 0.5 or above 0.05? And this difference here is the one that concerned me as a robotic vision researcher, in that whenever we visualize our object detection results, we use the 0.5 threshold, but because it gives us higher MAP, we use a 0.05 label threshold in order to get our final results. And in general, this doesn't matter too much in the context of a challenge, because you're trying to optimize your score for a challenge. But when trying to apply a system, should we be applying methods that have the highest MAP score? What if the highest MAP score is developed using a method that gives us all these false positives? If we don't have an understanding of exactly what meaning we should be interpreting from these MAP scores, we could have potentially catastrophic consequences when directly applying these detectors to real-world situations. Now, that was a bit of a bummer, and I hope that it's not sounded too much like MAP and the way that we're doing things now is inherently wrong. It's just that there are limitations there that I'm not sure that we as a research community are fully aware of. But I want to move past what issues might exist now and talk more about how we can try and address these issues moving forward into the future. These are just my views on the matter, but I feel like we should try and increase a focus on the application of object detection systems, and to that end, make sure that our evaluation procedures are fit to purpose for that final application. It's been very useful for us to be able to rapidly develop the general concept of object detection to the state that it is now using lots of predefined data sets, but we need to make sure that our object detection systems are accommodating for what their final use is going to be. If it is a low risk situation, such as labeling objects for a Google image search versus something being applied to a robotic system, this should be inherent in the overall object detection evaluation system, and it should be made clear what such a system can and cannot be good for when applied in the real world. I think there should be an increased awareness of any limitations for any evaluation measure that we use, not just mean average precision, so that we understand more fully and get a more holistic understanding of exactly how well our object detectors are doing at the various aspects of object detection. I would encourage the fine-grained analysis of object detectors, looking at the specific tasks inherent within object detection, aka localization accuracies and label calibration. The truth of the matter is we could possibly do with reassessing exactly what evaluation measures we do and do not use for object detection, both alongside and instead of MAP for certain given applications. Now, when it comes to new evaluation measures, I would just like to give a small talk about the insights that I have gained and my research group has gained when trying to create evaluation measures for robotic vision challenges, and how these can provide some benefits that might not be seen in normal object detection evaluation, and how these could be easily transferred from our specific robotic vision domain to a more general computer vision one. So within our research, we have ended up creating two evaluation measures, one for probabilistic object detection, called the probability-based detection quality, or PDQ, and one for scene understanding, specifically semantic SLAM and scene change detection, the evaluation measure being object map quality, or OMQ. Now, OMQ is very much just a refurbished version of PDQ, but for a different setting. So I would like to talk a little bit about PDQ, how we came about it, some of its benefits, some of its detriments, and how it might serve as some guidance as we move forward to creating new evaluation measures. So what PDQ essentially tries to do is it tries to establish whether or not a given detection for a given object describes that object well, both spatially and semantically. And the main difference between this and object detection is that the spatial aspect isn't given by a certain bounding box, but by an uncertain bounding box, a probabilistic bounding box, and label uncertainty is given as a full label probability distribution rather than a single class with a class score. Now, that is not the only difference in PDQ to object detection evaluation measures such as MAP. The principal difference between them, I would say, in their construction is that unlike MAP, which is trying to create precision recall curves with absolute true positives, false positives, and false negatives, there are no absolute true positives in PDQ. In PDQ, every detection for any given object can be said to have some degree of accuracy at describing that object. False positives only occur when, for a given detection and object pairing, there is absolutely no association. There is no quality score between them. And this quality idea, this idea that there is a degree of success in identifying what and where the object is what is used in the entirety of PDQ evaluation. So in PDQ, in a nutshell, we are simply calculating the average of all of these individual quality scores for paired detections and objects. And this is averaged over the number of, quotes, true positives, false negatives, and false positives that we have collected. So this quality score is what we refer to as the pairwise PDQ score, or PPDQ. And you can see that it is made up of two components. It is made up of spatial and label qualities. And these have their own formulations and ways about calculating them. And some of them even have their own subcomponents. Now, what is really cool about PDQ is that not only do we not have any absolutes, because every detection object pairing is said to be just some degree of correct and wrong. But we're also able to break down this quality score into its subcomponents, looking at how good we are at calculating where things are, what things are, and seeing what explicit values have influenced the overall PDQ score. This means that we can actually get quite a few submeasures out of PDQ. We've got PDQ, we've got our average overall quality, so the average pairwise score that we've gotten for all of our quote true positives, our average spatial quality, our average label quality. We can even look at foreground and background quality. We can look at the number of true positives, and false negatives, because we aren't dealing with a gradual increase in true positives, false negatives over time, in the case of a PR curve. And as newly introduced in iOS 2019, we can also calculate how good our false positives are, aka, are we overconfident whenever we're wrong? And not only do we have these measures and submeasures, but we can apply them not only across the entire dataset, but also on a per detection basis. We are able to see exactly how good is this detection of a fire hydrant, both spatially and semantically. How well have we detected this toilet spatially and semantically, and so on. So you can get a really nice fine-grained analysis in PDQ, particularly with extra tools that we've developed to allow for increased even qualitative analysis with some quantitative numbers. But so PDQ is our solution to how we could evaluate probabilistic object detection, probabilistic object detectors, but it is by no means a perfect metric. There are certainly some good benefits to it that I think I've highlighted. It was the first evaluation measure for probabilistic object detection for a start, but it also had no thresholds that defined success. There were no absolutes. All of the components of PDQ could be easily interpreted, and we could use our subcomponents of PDQ to look at individual aspects of object detection. And we could not only do dataset-wise, but also detection-wise analysis. However, there are still very much limitations to PDQ. There is no label calibration considered, which is, in my mind, a very important aspect of object detection. It doesn't work for open set problems. It doesn't consider that as an issue. It's still very much a closed set system. Until the introduction of false positive quality, all the false positives were weighted equally. And there are, frankly, just some simple exploits that people have found, such as making bounding boxes slightly smaller than the true bounding box for their uncertainty measures to give them better spatial quality. So by no means is PDQ a perfect evaluation measure. And in fact, I think that the search for a perfect evaluation measure might in fact be part of the issue. But it does give us a certain degree of a certain extra set of tools that we don't really see in object detection present. And this could in fact be converted to classical object detectors that don't have spatial uncertainty very easily. Just by simply changing the spatial quality measure to IOU, you'd have something approximating what PDQ is able to offer, but for a classical object detector. Being able to get all of these subcomponents, being able to look at exactly how many true positives, false negatives are created, etc. So again, I'm hoping that this isn't me laying down the law of what we definitely should be doing now, but it's directions that we could go in if we choose to. And I'd be very interested in discussions afterwards, in interactive sessions, and in the future to see how we can improve how we go about evaluating object detectors. So in summary, what I hope that I've conveyed here is that our standard quantitative analysis methods have been of great benefit to object detection research. It has given us great progress and the ability to easily compare methods, but there are still some limitations that exist when we can, particularly when we consider the final application of such systems. I feel like we should work towards improving our understanding of how our detectors are improving over time, as opposed to just saying they are and being able to see that one bold MAP number steadily increase. And I have tried to show some early examples of alternative approaches to detector evaluation that hopefully can help guide us as we move forward in this research field. I'd like to thank you very much for listening to what has probably been a quite long, rambly talk. I'd encourage you to come to the interactive sessions if you have questions about this, or if you have your own opinions, if you quite simply think that I'm wrong and would like to tell me why. I'd be very much interested in hearing. I've got a few interesting, useful links for you if you want to find out more about robotic vision challenges, about PDQ in specific, and some extra videos that you can go to for information on probabilistic object detection. Thank you very much for your time, and I hope to talk to you later. Thanks.